Hello, my name is Alexander Sehlström, and I will give you a brief overview of mine and Chris Williams' paper, The Analytic and Numerical Form Finding of Minimal Surfaces and Their Application as Shell Structures. Soap film have virtually no thickness, and therefore virtually no weight, and can be used to physically form find minimal surfaces. Fröjota knew this and made a very large number of soap film models to form find his many cable net structures. He used to materialize his soap film models using equal mesh nets. Equal mesh nets have quadrilateral faces whose sides are of equal length, but the faces must not be squares. However, it is only possible to approximate a minimal surface with an equal mesh net. Form-finding principal curvature cable nets are also relevant for other non-minimal surfaces which have negative Gaussian curvature. These can be considered approximately minimal and include compressed structures such as fan walls, cooling towers, and others. Any non-flat surface have curvature, and we may quantify this in several ways. The principal curvatures are the maximum and minimum values of the normal curvature of the surface. From these values, we get the mean curvature, the Gaussian curvature, and the radius of Morse circle of curvature. For minimal surfaces, the principal curvatures are equal but of opposite sign, and therefore the mean curvature is 0 and the Gaussian curvature is negative. These expressions are some of the more important things from classical differential geometry, which allows us to calculate distances on the surface and how the normal varies. With a net of cables following principal curvature directions, it is possible to produce true pretension minimal surfaces, subjected only to the limitation of the fineness of the grid. The net will then form a pattern of curvilinear squares, and any free boundary must follow an asymptotic curve on the surface. These are curves where the normal curvature is 0, and, as can be shown using Morse circle of curvature, the asymptotic directions are always oriented at 45-degree angle to the principal curvature directions on a minimal surface. A minimal surface can be mapped to other representations than its physical three-dimensional one, making the study of some of its properties easier. In a previous paper, we have described how a minimal surface with principal curvature coordinates can be constructed analytically expressed using a single function of a complex variable. This is a special case of the Weierstrass-Ennepeer parametrization, where we make use of information from the Gauss map to align the coordinate curves with principal directions. If a cable net is constructed following principal curvature directions on a minimal surface with constant force density, the cable net will be in static equilibrium. This fact can be used to, in a very simple way, numerically form find the surface and the principal curvature net simultaneously. The force density is the element tension divided by the element length. And if the covariant base vectors are aligned with the principal curvature directions, the vector representing the force in each element is simply the force density multiplied with the covariant base vector. This movie shows the form-finding procedure for a portion of the surface connected to the rest of the surface via symmetry. The tension coefficient can be set arbitrary, so as a convergent criterion, we may study the ratio between the sum of the element lengths in one direction and the sum of the element lengths in the other. We do this for both the principal curvature directions and the asymptotic directions. In addition to moving the nodes around during the form finding, we move the position of the support slowly upwards and the free edge slowly outwards. This is a variation of Plateau's problem, where not only the minimal surface through a given boundary is found, but also the boundary itself. Our numerical implementation relies on dynamic relaxation, and we have written a kernel that can compute updates for multiple nodes in parallel. This enables fast parallel computation on the GPU rather than slow serial computation on the CPU. Our tests show up to 15 times speed improvements for simple integrated GPU cards, up to over 120 times using a dedicated graphics card. Numerical form finding requires an initial grid or cutting pattern. And if we start with the regular grid, the verticals and the horizontals will map to principal curvature directions, whereas diagonals to asymptotic directions. Therefore, any free cable must be defined as a diagonal line in the initial grid. To the left, the principles for the cutting pattern used for the shell in the previous slide is illustrated, and to the right for a part of Mesmeki's concrete shell bridge. Running the code, we obtain the following result for Mesmeki's bridge. To the left, the principal curvature lines are drawn, and to the right, the asymptotic. Of course, further tweaks are needed, such as tuning the tension in the edge cable and adding self-weight to obtain the correct shape. We would like to end this presentation with some remarks about our interest in asymptotic directions. And this applies not only to minimal surfaces, but to any surface with negative Gaussian curvature, which, as mentioned before, can be considered approximately minimal. So, of the objects in this picture, it applies to the entire hyperbolic paraboloid-shaped crisp and parts of the banana with negative Gaussian curvature. If the points are chosen carefully so that we can find asymptotic curves running between the loading points and the support points, the loads will be transferred through the surface as a force couple along with the asymptotic curves. The rest of the surface will, in theory, remain stress-free. With no other loads on the surface, the forces along with the asymptotic curves are constant, but the slight difference in their direction effectively causes the force couple to form a moment. The asymptotic curves of the crisp are straight lines, so they diverge linearly and therefore the moment varies linearly. But in general, the asymptotic curves are not straight lines, so the moment will vary non-linearly. That is the case for the minimal surface we discussed earlier. Thus, a grid shell with members following asymptotic lines on a doubly curved surface will transfer loads only through axial forces along the members and do, in theory, not rely on bending capacity. And we may use this fact to construct not only minimal surfaces carrying member stresses in tension, but also those carrying compressive stresses, or a combination of the two. We look forward to discuss our paper further with you and would like to thank you for listening.